Good afternoon, everybody. Today, we're going to talk about the just finished USACO 2023 December contest, Platinum level problem number 1, cow contact tracing. The problem is like this. Farmer John has N cows. Some of them are infected. Which cow is infected is in this binary string, 1 or 0. Then every night, the cow are connected with each other through a tree structure, as the edges are described like this. Every night, infected cow will infect its neighbor. So at some amount of night, Farmer John realized their farm is infected. So, and then you're given Q number of nights, and then that's the night Farmer John determined their cow is affected. The question is, what's the minimum number of cows that could start the illness? Or if that's inconsistent with information, give -1. First thing we will, so this is a query, right? Query of N. Remember, they already gave us the nights we need to look at. So we actually don't have to do query in the order they gave, right? If I can just figure out, from 0 to N for each night, what is amount infected, that would be much easier for me to do. So maybe I'll do this query as an offline process. So then let's look at some examples. The first example is I have a tree which is 1 goes to 2, which goes to 3, which goes to 4, which goes to 5. So if for the first night, right? If the first night Farmer John determined there's a cow, that is, the cow is affected, obviously, every cow needs to be infected, right? So if it's past 1 night, that means if I have this cow and this cow are initially sick, then after 1 night, it will infect the neighbor, right? Then Farmer John will determine it. So that means you got to have 2 of them from the beginning. If you look at the 3rd night, then, second night, then I can have this cow, right, infected. Then 1 night, 2 night, right, same here, 1 night, 2 night. So I only need to have 1 cow. It's sick initially. So this is the example. Then let's look at the second example. It's like this. 1 goes to 2, 2 goes to 3, 4, 5, 6, 6 goes to 7, 7 goes to 8, 8 goes to 9, 9 goes to 10. The same thing, right? If it's the initial night, everything has to be infected. If it's the first night, if I want to maximize the coverage, greedily, obviously, I'll choose this as an initially affected cow. Then after 1 night, all those will be infected. But those are not. So I should choose, for example, this cow. 1 night it will infect this and this. Then I need to choose this cow, right? So I need to have three cows initially at day 1, right? So what about day 2? If it's 2 nights, so obviously I should choose this one. In day 1 will infect this. In day 2 will infect this. There's still 3 cows that will not achieve that. So I need to choose another cow in night 1. Night 1 it will infect this. So I need 2 cows, right? Then then that is in day two nights. So if I have 3 nights, first night it will infect this, and second night this cow will this is the first night, right? And the second night it will infect this. The third night it infect this. That's one way. The other way is I can do it the other way around, right? So I can have, because those can be achieved in 1, 2, so I can do initial cow is here, right? First night, second night, right? So if we want to do, sorry, we want to do 3 nights. What else? So if we want to do 3 nights, so see if I pick this one, right? First night, second night, third night. First night, second night, third night. So I only need 1. I can achieve that. Okay, so if you look at this problem, this reminds you what? This reminds you the centroid, right? So if we do a greedy algorithm to figure out what is the centroid that I need in order to identify those, then I can get maximum coverage. If you don't remember what centroid is, again, go to USACO guide from Benjamin J. And at the Platon level, there is a description of centroid decomposition. Okay, so the centroid decomposition basically go like this. Let's take this as example. Okay, so what does centroid do is, if you have a tree, right? So let's say you have a tree kind of like this, first you find a node that is on the left-hand side and the right-hand side. I mean, on either side, there you have almost as close to equal number of nodes as possible. So the way the algorithm works is, if you look at how to build a centroid, okay, build a centroid. So what you do is, when you build a centroid, you basically do an iteration, right? You find the centroid. You find the way to find the centroid is you go through each of this subnode. If the subnode is, the size is more than the other side, for example, if I start from here, okay, this side obviously have much more nodes than this side. Then I go here, right? At DFS, go here, then I go here, okay. Then I find, oh, this side is roughly the same size of that side. So that's my level 1 centroid. Then I go down over each of this branch. Here I find this is my level 2 centroid. This is my level 2 centroid. And here, this is my level 2 centroid, right? I mean, this one is not. So then I break down this. This is log n, right? Once you have the centroid, then if you look at the problem I have here, what I'm doing is, once you have the centroid, right, you can get to every node in log n time, and you break down into the easiest way to access. So if you look at the problem I have here, right? So I greedily find what is my level 1 centroid, for example. I mean, could be like this one. So then I pick that, right? Then I break down into it. So then the algorithm to do this is like this, right? If we have 0, the number of nights is 0 initially, obviously every node, every cow need to be infected. Then the first night is you identify, any of those trees, right? You identify the centroid. Let's say you start from the level 1 centroid, right, as I described up there, and you remove all the neighbors which is 1 distance away, okay, because those will be affected, right? Let's say here's another one. Those will be affected, okay? So maybe you have another, let's say another node like this. Let's say this is your another level 1 centroid thing. Okay, so what you left, so then how many centroid left here is the number of cows you need to have initially infected, right? Because those are the ones that can reach 1 step further. So let's say all those get removed. Then what you end up with, this is, right, so we do night equals 0. That is easy, right? Everything. Night equal to 1. This is what you left is, then I left with a tree which is just a centroid. Sorry. The tree just a centroid. Okay, let me just make it more complicated. Okay. The distance between those, you do it -1. Okay, so you left with a tree that is just centroid, and you know how far you can infect, right, from 1 centroid to another centroid. You do an offset. Then when you get night equal 2, then you imagine this is your tree again. Then you do another centroid on this. Okay, so in this case, that will be your centroid, and that could be your centroid. Okay, so then you're left with another tree, right? Which is, in that case, you only need 2 cows, right? So in that case, you're left with this, and you only need 1 cow. So you basically, what you do is you're using a greedy algorithm and use a centroid. So every night you're stepping up, you remove all the neighbor cows, and then you're left with a new tree, which are the original centroid. Then you redo this, and then you, end of the day, right? Then you get everything. Okay, so that will be an log n, right, algorithm. So this problem is not that difficult as long if you know how to do the centroid decomposition. Okay, that's a problem for today, and that's an algorithm. Please go, if you're not familiar with the centroid, go study the centroid decomposition and then try to solve the problem. If we look at the official solutions, they use a different approach, but in the end, they did tell you another way is to use centroid decomposition. That is the way when I did this, I started with that. That's the way I was thinking about that problem. Okay, Happy New Year, and hopefully you use this weekend to code it up. And we will see you in next week and talk about problem number 2.